Hello and welcome to the first in this series of lectures on integral calculus. This first lecture will be focused on the concept of indefinite integrals. This is a concept that you have seen already in high school, and therefore, as we have done before, I will be going fairly quickly over some of the aspects of the concept of indefinite integrals, but I will also focus on some aspects of it that you may know already but need to be highlighted and clarified, as well as at the end I will show you one little detail that probably you have not seen in high school. So in order to start having a look at indefinite integrals, let's start from what we know already. So in the course on differential calculus, we've seen that if I tell you what a function f of x is, and if a function f of x has a reasonable formula, then we can compute its derivative, which is denoted by f prime of x. So in this graph here you see in blue the function, the original function f of x, and its derivative f prime of x in red. By the way, as a little exercise for you, you may want to check that the features of f prime of x do match, in fact, the features of the function f of x. In other words, that the connection between the function and its derivative, as you can gather them from the graph, are what they should be. And it's a good exercise for you to remind yourself of what the derivative actually represents. Now, what we're going to be looking at now is this question: can we go backwards? That is, if I give you f prime of x, is it possible to construct the original function f of x? Now, again, you have seen this problem solved before, so you know that it can be done, and at least in some cases. So I'll be quickly going through a very quick argument for the fact that it can be done, at least in some cases. I'm not sure if you have seen the fact that it cannot be done in all cases, but if you haven't, well, we'll see that later on in one of the later lectures. So let's look at a simple example. So if I tell you that I have a function whose derivative is cosine x, and so the question is, do I know what is the original function? Well, we know that the derivative of sine x is cosine x. So in this case, at least in this case, we can reconstruct the original function, the original sine x. Okay, but of course you also probably know that if I consider the function sine x plus 3, well, that one also works. Okay, the derivative of sine x plus 3 is also cosine x. In fact, I can add any constant to my basic sine x guess, and it will still give me a function whose derivative is cosine x. So that tells us that in general the problem of finding a function whose derivative is the given one does not have a unique solution. So for each given derivative, we're going to end up with infinitely many functions that have that function as derivative. Okay, so it can be done, it has many solutions, and so on and so on. All right. So let's start setting some terminology so that we can speak about these objects without having to run in circles with complicated sequences of words. Okay, so first of all, if I give you a function f of x, then any function capital F of x whose derivative is the function I'm starting with is called an antiderivative of f of x. You'll notice that the notation I'm using here is starting to be a little bit complicated because I'm using lowercase f for the starting function. Well, that's because I don't really want to write it as f prime because I'm starting from a given function. I want to see if I can find a function whose derivative is the given one. Is this getting complicated? Well, it should. That's my point. We're trying to figure out here the fact that we do need a better notation and better terminology. So hopefully this will convince you of the importance of the notation and terminology I'm about to present to you, and that you're going to use it and use it properly. Now, also remember there is not one single antiderivative, but there is many. We can just add another constant. And so if we consider the set of all such functions, all functions whose derivative is the given one, then we're going to call this the general antiderivative. Okay? So as I said, the notation I've used right now is pretty much one that is also used in practice. You'll see it in books where you start from a function lowercase f of x, and you're trying to construct its antiderivative, and you call that capital F of x. But as you can tell, it's not really a good notation. So we need a better notation.